Thank you. Thanks for still staying here and still trying to be interested. Very nice. I'm going through this little bit introducing Güntner. Every good company starts with one person in a garage. Our founder started 1931 in his garage in Munich, and he worked out heat exchangers for Linde cooling in his first stage. But in the meantime, Güntner is a global player with international presence, and the core product heat exchanger is a very diverse product. It can be used for many, many applications, from food cooling, air cooling, up to climatization of buildings. But also a big part is the cooling of the energy transition. Short overview who we are. Actually, like I said, 95 years we are providing industry standards in the heat exchanger business. We have nowadays 7,000 people in our organization with a 700 million turnover in the last year. We are present in 50 countries with 11 manufacturing plants worldwide. So in Germany it's called a hidden champion, as I say, sometimes too hidden. So I'm here to say we do some good, so we talk about it. But what do we actually do? Where is our interfacing to the hydrogen industry? Basically, our product is the dry cooler or recooler, or as people call it. It is also the hidden component in all the installations. Nowadays, I saw a few slides and a few installations where people even pointed out, here is a recooler in the back of the unit. But fact is, it's a vital part. And we have different versions of this one in our portfolio. It's a table cooler as a very well-known product, but also the V-type cooler in all its glory. The difference between these units is there is a power density difference between these units because there are different heat exchanger coils within these units as well. And I want to show a little bit in this one where it is really used. So we saw already a few slides of packagers or system integrators, which is a very nice solution. You can see the dry cooler is standing together with a container. It is a mobile solution. It is a one-on-one solution that has a very big advantage. But it also has some limitations at the end of the day. One of my predecessors from Neumann and Esser had a very nice setup with his new 5 megawatt package. Also needs a large V-type cooler, but fact is, at the end of the day, a package like this has limitations. And this is where I want to talk about a little bit what needs to be considered when we want to scale up. We heard in the morning the need to scale up. There is a need in the market. There is enthusiasm in the market. There are large projects in the market, 3 gigawatt we saw on the map. But these are all 150, 200 megawatt electrolyzer plants. There we have to think different. And actually, I chose this picture here because this is a generic picture. It's hard to get real pictures from real large installations. That's number one. Number two is there are not so many of these ones. And this means that large plants actually have also large challenges. That's a little bit idealized on this one. So we had a few projects that we worked on in the past, and a little bit experience point on this one, what needs to be considered by this vital part of cooling. And there are 3 parameters that actually really need to be considered in a different way as they, for example, need to be considered from a system integrator. And these 3 are, of course, performance. They are sound. We are really surprised how much sound actually defines a system. And of course, location. Location, location, location. It's like real estate. Let's start with performance. And the first thing that we need to understand when it comes to cooling systems is that a dry cooler like this is actually defined by its thermodynamic physics. What does it mean? We have a cooling circuit on one side and we have air on the other side. So the fluid has a thermodynamic, the air has a thermodynamic, and it has to match together. There are formulas, there are heat transfer coefficients, etc. and so on. It's physics at the end of the day. But I show you this picture here because this is a very seldom glimpse that people get into the core of a heat exchanger. We have here a block of fin lamelles which are pre-stacked, and then we put the tubes into these lamelles to build a heat exchanger coil. It has its limitations. To give you an idea, the picture looks big, but the largest side that actually makes sense for a dry cooler is that the height of this coil, what you see here in the front, is maximum 250 millimeter. Why is it like this? Because that's the way how you can get most surface of fins into a construction of steel that a dry cooler actually is. So when we talk about performance, we are bound by the physics. We know how the formula is, we know how the algorithms are, we know what we can build from the construction side. So with this one, we can actually answer how many square meter of these fins do I need to pack into my dry cooler in order to reach the performance of this one. And once we know this, we also know how many dry coolers we actually need. And that is more than just one dry cooler that stands on top of a container. To give you a rough idea, a 50 megawatt electrolyzer plant needs between 24 to 30 megawatt cooling capacity. Sounds a lot. That's energy that it needs to be dissipated. In the large V-types that I showed on the picture before, you can pack up to 3 megawatt. It depends on the temperatures that you are using at the end of the day. Nowadays, the industry standard says that you actually can only pack maybe 1.5, 1.8 megawatt into one of the large V-type coolers. So when you need 22 megawatt, you can do the math. It's about 21, 24, 25 units that you actually need of a large dry cooler. That needs to be kept in mind, because the next point is sound. Sound is generated by the moving air and by the rotating equipment. On the cooling plant, basically it means the only sound emitting element is a fan. It's not the cooler itself, it's also not the electrolyzer that is sound emitting. It is really how many fans do I actually have running on my cooler. And this is what I know by how much air do I actually have to move on a large scale plant. We talk about 100,000 of cubic meter per unit. And that's why I chose a picture like this as well, because you see there are many, many fans on one unit. And now you just have to think, you multiply by 21, 22, 24 units, how many fans do I actually have? It's a lot of fans. Again, physics. Sound is calculated by logarithmic addition. So you add up very quickly on a very loud plant, normally. And that's why I say sound is one of the most defining factor of larger upscaled cooling plants. Because here, one thing comes into place, and that's regulation. People nowadays, of course, they like to have it nice and quiet, even in an industrial area, and the regulations are very strict nowadays. It's environmental emission. Sound is noise, and noise can make sick. We know that, and that's why these regulations are in place. But that's still the question. I have 100,000 cubic meter of air that I have to move over a heat exchanger, and I have so many fans that are running at the same time. How do I control my air? How do I control my sound as well? Well, you can control over speed. The speed of the fans is basically giving you then the idea what is the sound emission of your cooling plant. That's one of the parameters, one of the challenges you see. Yeah? So you need so many units, but you are only allowed to run the fans in that kind of speed. And how does it fit together? It's basically multiplying and finding the speed spot on this one. But now the wildcard comes into place. And that's location, because planning, again, a generic picture, always looks nice. We have everything here on a green field. We have a large electrolyzer plant. The gas station is there. The gas treatment is there. Some of the renewables energy is there. I don't see a cooling plant on this one. So there's no sound emission. There's nothing considered for that one. But fact is that reality often looks like this. We have existing installations, and once the planning is through, the project is coming to financial closure. Something must be really realized on this one. Then you get a layout like this. and at the end of the day, the project owner says to you, well, you have this brown area on the top there, and that's where everything has to fit. How to do? You have to balance between all these things. Somehow, you always find a solution about this because you have to at the end of the day, but it's not as easy as it seems on the paper. And that's what I want to say by scaling cooling systems. Scaling is not multiplying things. Scaling is actually looking into the details, especially when it comes to the balance of plant. So when I talk about plant integration, it is just more than the product, because the product looks in a simulation nice and easy. It comes from an idea to a concept, because here you need to consider how can you stack things together. How can you lift it up so that everything works, that the performance is there? How do you get your air? And it is a long way until you get a final plant on an installation. This one is an installation to give you an idea in the Scandinavics. I cannot give you the full picture, unfortunately. It looks nice, but it also looks massive. And at the end of the day, this is where we have to go on large-scale plants. So, making it short now, basically, we need 3 components together. This is know-how. The know-how is on the EPC contractor side, on the engineering side, on us as a component supplier. We need concepts and options. There are many options available how a dry cooler can look like. It can be table type, can be V-type, can be an adiabatic cooler, can be a dry cooler. It all has advantages and disadvantages. But more important, it needs project management from the start until the end. We need to talk to each other in order to find out where is the sweet spot on each and every project. So electrolysers can be scalable, easy, standard product. We heard a lot about this one today. But for the balance of plant, it looks a little bit different. It really is worth to look into the details. And for this one, I think we can support. We are here. We have the know-how, 95 years experience. We did a few installations in that scale already. And I think with this one, my time is actually up. And I would like to say thank you.
Thank you very much, Oliver. Yes, we have a little bit of time for a few questions here. So, and the first question that we see here is addressed: how does the design of the cooling system affect OPEX over the plant's lifetime?
Well, it's of course a good question. Again, finding the sweet spot is difficult. Large plants have large capex, can have low OPEX. Small plants, compact plants with, for example, adiabatic solutions have higher OPEX cost because you need to consider, for example, additional water treatment for the adiabatic solution, where you spray water on the heat exchanger in order to get a more compact design about this one. So it's very difficult to say, but the rule of thumb is the larger your approach temperature between your design point to your cooling plant is, the more compact the plant will get, and the more reduced the OPEX cost can be. Okay. And the second point is there, of course, regulation.
Yes.
What needs to be done that can easily blow up a plant and that can easily blow up OPEX costs.
Okay, yes. And about maintenance, is there also something that we should actually...
well, a cooling plant like this has one time per year maintenance.
Yes.
Actually, we have a few tools for our units where you can do predictive maintenance.
Yes,
we work with AI tools on this one, like data collection. So it can help to lower the OPEX cost from the standard one, because it doesn't help when your service guy goes to the plant and has to go a second time because he forgot to fix one of the fan, for example.
Yeah. Okay. And then we have the last one here, which is that someone is impressed by these type of V-type coolers. And can we actually have also some other heat exchangers matching to district heating, for example?
Very good question, and the simple answer is yes, because our heat exchangers are also used in district heating applications as air-charged heat pump, air powered heat
Heat pump.
pump heat exchangers. The application for the heat exchangers is very versatile. There we can really go into engineering details about this one. At the end of the day, it helps to bring energy from A to B.
Yes.
And like I say, the application is diverse. We are open for anything on this one.
Perfect. Okay, Oliver, we are done. All the questions have been answered. This is, leading to a big applause. Yes, thank you very much.
Thank you.
Dr. Oliver Bröldiek, Business Unit Leader from the Güntner GmbH. Thank you very much.
Thanks for your time.